Hello physicists and welcome. In this session we'll be covering practice 12, quantitative calculations and proportional reasoning, found on page 19 of your packet. Let's get started. Hey, so we have this scenario. A bowling ball is thrown by a professional bowler and travels down the lane at 8 meters per second. How far will the ball travel in 2.5 seconds? What I'd like to do is always have a picture of what I'm doing first. So we'll have our bowler here with the ball and heading down the lane, probably toward pins down here. All right, and we're going to call to the right our positive direction. All right. Hey, what are we looking for? Hey, so we want to know how far. So what we're looking for is our displacement, delta x. In the problem, I've given some information. What am I given? I'm given that it's thrown by a professional bowler, travels down the lane at, my velocity is, here it is, 8 meters per second. And we're going to be traveling for 2.5 seconds. Hey, next we want an equation or a relationship that contains what we're looking for, our displacement, in terms of the things that we already know. And so I have this equation that my velocity is equal to my displacement divided by my change in time. And what I'm interested in doing now is isolating the variable. The variable we want to find right now is our displacement. So to take care of that, I'll multiply each side by t. We could also say delta t. Those cancel. So I have this, let's say, velocity times my change in time is equal to my change of position. Let's go ahead and solve that. We'll put in the numbers we have. My velocity, 8 meters per second. Our change in time from the time I release to the time it hits, or it's down the lane, 2.5 seconds. Let me write that in here. Where am I? Here I go. 2.5 seconds. 8 meters per second times 2.5 seconds, I get 20 meters. Hey, so by proportions or ratios, let's go ahead and solve scenario B. If the ball was thrown by a child at 4 meters per second, how far would it travel in the same 2.5 seconds? Let's go ahead and we'll do that by proportional reasoning. Hey, so let's take a look. What are we looking for? How far? So I'll circle that. Looking for how far it'll go. Thrown at 4 meters per second. Let's look at the ratio on our velocity. So we're now at 4 meters per second compared to our pro bowler's 8 meters per second. So our ratio is 1/2, or another way of saying that the child can only throw the ball half as fast as our professional. So our velocity is 1/2, and notice it's in the same 2.5 seconds. When we're looking at same, our ratio or proportion for that is 1. So that tells us that our proportion of displacement is 1/2. We're going to transfer that down over here. So my coefficient stays 1/2, the variable that we're looking at, displacement, delta x. So I'm going to carry that coefficient over here. 1/2, the original value, delta x, I pick up over here, 20 meters times 20 meters. My new value, 1/2 times 20, is 10 meters. So I can expect the ball thrown by that child would go 10 meters in that same 2.5 seconds. Let me put in a little written description. So I could say that, hey, if a bowling ball is thrown at 4 versus 8 meters per second, so another way of saying is that half speed, the ball will travel half as far. Makes sense. Okay, and that was 10 versus 20 meters in the same time. All right, nice written description of that. In this last section, we need to sketch a velocity versus time graph for each motion. We can show that displacement on the graph and then use the graph to calculate the displacement. Let's first look at the pro. Hey, the pro was throwing the ball at 8 meters per second and it rolled for 2.5 seconds. So that pro is throwing the ball like that. That describes the velocity of the ball. We'll assume that as it goes down the lane, it doesn't lose any speed. For the child, the velocity is 4 meters per second, again for 2.5 seconds. 1, 2.5, 2.5 seconds. Hey, next thing, we want to show that displacement on each graph. And remember that displacement we can figure out by looking at the area. I want to use the fancy term area under the curve. So it's this area here, because we know that displacement is our velocity times our time. For a rectangle, the area of that rectangle is its height times its base. I'll do that same thing for our ball thrown by the child here. That area represents the displacement. Now, the last thing we have to do here is to use the graph to calculate the displacement. Hey, we know that our displacement is equal to velocity, the height of our rectangle, times time, the width of our rectangle. Let's go ahead and calculate that for our pro. Our pro, we're going to take the numbers right off here, is 8 meters per second times 2.5 seconds equals 20 meters, which is the area of this rectangle. And lastly, let's do it for our child. Okay, we know again it's our displacement is equal to velocity times time, which is the height and width of this rectangle. For the child, that is 4 meters per second times 2.5 seconds. 4 times 2.5 is 10. Meters per second times seconds gives us meters, 10 meters. And there we have it.